I should also be recording. Right. Is the audio better? Shouldn't be a lot of background noise. There's nothing happening in the background. Better? No? Okay. Okay. Oh, I know what it is. It's my tablet's fan, I guess. So let me figure out a way to prop it up. Oh. This will work. Oh no, everything's going wrong. Is this better? Better or worse? All right, I'll just have to write gently because it's kind of like balancing on its stand. All right, so and let me put these back. All right, so the gravitational potential energy formula that we gave last time, that relied on the vertical direction, the up direction being the y direction. And that matters because if I had chosen a different, if I had chosen x to be the vertical direction, for example, then the potential energy function would be different. But regardless, in this coordinate system, we have that the gravitational potential energy function for an object of mass m is mgy. So let's check. Let's check that the force is exactly what we expect it to be. So the force would be the negative partial derivative with respect to x of mgy in the I hat direction minus the partial derivative with respect to y of mgy in the j hat direction minus the partial derivative with respect to z of mgy in the k hat direction. Okay. Hopefully the sound didn't kick up again because the fan just kicked on. So we talked about how partial derivatives work last time, or maybe it was on Wednesday. No, definitely last time. And so recall that when you take a partial derivative, say with respect to x, you treat every other variable, in this case y and z, as if they were constant. So this term, well, mgy is treated as a constant, and the derivative of a constant is 0. So that term would be 0, and this last term would also be 0. The only term that wouldn't be 0, the last term would be 0 because we treat x and y like a constant, because we're taking a partial with respect to z. The only term that wouldn't be 0 is this middle one, and that's because if we treat x and z as if they were constants, then there's still a y there, so you have to take the derivative like you normally would. So this would be equal to minus mg, and the y disappears because we're taking a derivative, in the j hat direction. And voila, that is exactly what we expect it to be for gravity. Gravity should point in the negative y direction because the y direction, is the up direction. And it should have magnitude mg. So that checks out. That's good. Just as an aside, we could have just as easily could have equally well used a different gravitational potential energy. We could have also used the potential energy mgy plus, say, u naught, where u naught's just some number, like it's just a constant. And the reason we can do that is because the partial derivative of, say, u naught with respect to x is 0, as the partial derivative with respect to y, the partial with respect to z. The partial derivative of a constant is always 0. So the force that we get out at the end of the day doesn't care if you add a constant to your potential energy function. This gets back to the point I was making on Friday, that you can always add any constant you want to the potential energy function. That's always okay, because at the end of the day, the only thing we actually care about are the forces and changes in potential energy. And changes in potential energy don't care at all about the constants that you add because they would cancel out. So let's do another example. Let's do a spring that's displaced in the displaced along the x-axis. So imagine that the spring is like coiled up along the x-axis, and then we like stretch it along the x-axis. So in that case, we can write down the potential energy function for the elastic force. We did this again on Friday, and it's equal to 1/2 k times x minus x naught squared. Now remember, this x naught is the position, or it's the equilibrium. Yeah, it's the x coordinate of the equilibrium position. But the equilibrium position is on the x-axis, so this is just like the equilibrium length. So that's the position that it would have to be at in order for there to be no force. That's the position the spring is happy at. And then this x, that's just the position of the object that we're interested in. And let me write this as a function of x, y, and z, because they always are. So that x is just the position of whatever object of mass m we're talking about. All right, so let's do this again. Let's take can you write delta x instead of that in the parentheses? No, because then it wouldn't be obvious that it's a function of x. So the reason why so delta x is k is the spring constant. It's basically how stiff the spring is. The reason why we use the square the difference? No, it's the difference squared. Veridia, I'm gonna mute you because reasons. So go back and check your notes on Friday. This was the potential energy function for a spring. The reason for that, and the reason why we don't use delta x, is because we want to make explicit the functional dependence on the coordinate variables, on x, y, and z. Delta x it's not really clear what delta x, like what would the partial derivative of delta x be, right? And we want to be able to do that. Right. All right, so let's take the partial derivative and find the elastic force. Now that should be a sub g up there. So this is what the elastic force would be for a spring that has equilibrium position along the x-axis and is stretched along the x-axis, or compressed. So we would take partial derivatives, or the negative partial derivatives of the function of 1/2 k x minus x naught quantity squared. This is in the I hat direction, minus partial derivatives with respect to y of 1/2 k x minus x naught quantity squared, the j hat direction, minus partial derivative with respect to z of 1/2 k x minus x naught quantity squared in the k hat direction. All right, now again, we know how to wire their, that's the definition, or that's the formula for how to go from potential energy functions to forces. Basically, it boils down to the fact that the potential energy was the negative of a work that's done. And so the work is the integral of a force. So that's where the negative sign comes from. It's just a convention for how we define potential energy. And it makes sense because then forces point towards lower potential energy rather than towards higher potential energy. That's all. Right, so partial derivatives with respect to x, the partial derivative with respect to y of something that doesn't depend on y, it only has x's and other constants, that's just 0. And similarly, for the z component, it's also just 0 because there's no z's in that function. So we're only left with this term. And you guys can work out the derivative. It works out that it's negative k times x minus x naught in the I hat direction. And that is precisely the elastic force for a spring that lies along the x-axis. You can go back and check what our elastic force was. And the only difference between what we have here and what we had before was that we had vectors on these. But the vectors in this specific case would be in the I hat direction. So you can see how before x vector was x in the would be equal to x in the I hat direction, and x naught vector would be x naught in the I hat direction. And so you can see how these two things are the same. So sometimes, so in general, you only have to worry about the force, the partial derivatives when the function actually depends on, yeah, I mean, it is just the gradient. It's the negative gradient of U elastic. That's true. Yes, U elastic is the potential energy function. So in general, like, I didn't actually have to write these terms because there was no z present in this potential energy function. I was just doing it for completeness. Like I could have just ignored the y and z component because I know that the potential energy, that the partial derivatives of those terms is 0 because there is no y and z in this function. But I was just doing this, again, I was just doing it just to better elaborate on how this works. So we went over that on Friday, but I will give you another example. So you'll see a way to find potential energy functions in a minute. So first let's answer the question: how do we determine, or how can we find if a force is conservative? Sorry, if a force is non-conservative. So we now have this tool that says any conservative force has a potential energy function and vice versa. So if we can write down a force that that there is no possible potential energy function that gives that force, then we know that force is not conservative. And when I say there's no possible potential energy function that gives that force, what I mean is there is no function u of x, y, and z such that if you take its negative gradient, you get that force. Like there's no function that you can take the negative gradient of to get the force back that you want. That would imply that the force is not conservative. So there's a few steps that we can, or there's 2 steps that we can write down to do this. So the first step is we integrate the x component of the force. So the assumption here is you're given some force and you want to find if it's non-conservative. By the way, this will also work to determine the potential energy function if assuming a force is conservative. So these techniques I'm about to lay out kind of answer 2 questions. Right, so we would integrate the x component of the force, and it could be the y component or the z component. I'm just choosing the x component to get a general function for the potential energy that works for that component. I should actually say anti-differentiate. That'd be more correct. Anti-differentiate. That works for that component. I'm going to go through an example for this, by the way. So the first thing is noting that you know that if there is a potential energy function for the force that you're investigating, then you know that taking the partial derivative with respect to x will give you the x component of the force. So if you're given a force, just take the x component of that force and then integrate it with respect to x, and that should at least give a general picture of what that potential energy function should be if such a thing exists. You will always get an answer for the antiderivative, but sometimes that answer won't work for the other components of the forces. And again, you'll see more how this works in a minute. Step 2. So after you anti-differentiate to get a general potential energy function, you just check that the candidate potential energy function, which is the one that we just generated by taking the antiderivative, works for the other components. So once you generate your candidate potential energy function, you then take the partial derivative with respect to the other coordinates, y and z, say, and check to see if they can match with what those force components actually are. If they can, then you're done. You have a potential energy function for a conservative force. If they can't, if no possible function exists that will let you do that, then you're out of luck and there is no potential energy function for this force. And that means that the force is non-conservative. So let's just run by an example. So is the force F, which is equal to xy, or let's say axy, where a is a constant, axy in the I hat direction conservative? So let's just test this method. So first of all, it's safe to say that if F is conservative, then let me write this out in words. If F is conservative, i.e. if such a potential energy function exists, then it shouldn't really depend on the y or on the z axis. Which is to say, if it doesn't work, then it's non-conservative, precisely. Right, so the point that I'm making here is that there are no z's and there's no k hats present in this force. So whatever potential energy function it is, it shouldn't at all depend, there should be no z's present. Like, there should only be z's if you need to get a k component or if a z pops up in the force, in the formula for the force. So we're just going to assume that our potential energy function, if it exists, has an x or is just a function of x and y. So we're just going to work in the xy plane. So step 1 says integrate the x component. Now again, like I said, there's nothing special about the x component. It's just a choice. I could also do this for the y component. Yeah, sure, why not? So the x component of this force is axy, and according to our definition of according to the formula to get the force from the potential energy function, this should be equal to the negative partial derivative of the potential energy function with respect to x, right? If such a u exists. So that would imply that the potential energy function with respect to you can undo a derivative with an integral, right? So this should be equal to, well, I would have to integrate this, should be equal to the negative integral of axy dx. I'm just undoing this partial derivative by taking an integral. Now we have to be careful here. So first of all, y is just a constant with respect to x, so this would just give us negative 1/2 ax squared y, because we just treat a and y as constants. But we have to do something special here. When you do an antiderivative, you always have to add a constant, right? Like if you did like integral of x dx, that's 1/2 x squared plus c, right? But here, in this case, it's not enough to just make it it's not enough to just add a constant, because there is another coordinate variable, another thing that could change if you changed y, but we're not changing y. So instead, we add a function that's constant with respect to x. Right, it's precisely that, Hannah. So so all we do when we do this antiderivative is we add something that's constant with respect to x, i.e. if you change x, the thing you add doesn't change. But you can still add something that changes with respect to y, and that doesn't break anything. I.e., if you were to take the partial derivative of this, you will get axy back, because y doesn't depend on x. Right. Okay, so this is our candidate. This is our candidate potential energy function. And f is just some function. It's just some random function. We don't know what it is. It's just some function. Step 2. Step 2 says test it on the other components. All right, so we know that the y component is 0, right? And so this is supposed to be equal to, or rather we're wondering whether this is equal to the negative partial derivative of our candidate. Negative 1/2 ax squared y plus f of y. We want to know if this is possible, if this equality is possible to be true, if it's possible that there is some function f of y such that if you take the negative partial derivative of it with respect to y, you get 0, then we're done. Then this is a check mark. It's indeed conservative. And so we can just do this partial derivative. This would give this would give 1/2 ax squared, because we take the derivative of ax squared y, treat x like a constant. And then we have minus f prime of y. And that prime just means derivative, because y only has one variable, so the prime it's not vague what the prime means. It just means derivative of that function. And so this is supposed to be equal to 0. Now, there's trouble. So that would mean that if this was possible, that would mean that f prime of y equals 1/2 ax squared. But note, y is supposed to, or f of y is not supposed to depend on x. it should only depend on y and maybe other constants. And so this is wrong. It doesn't work. There is no function f prime of y that has to be equal to 1/2 ax squared, because if the derivative depends on x, then the function has to depend on x, right? So there is no way. So there is no function. There is no function u of x and y that is a potential for f. Potential energy for the force f. It's not that it was set to 0. It's that we were given the force. The force was given, and it has a, like, the y component is 0 and the x component is axy. We could have done this in the reverse order, but it would have been harder. That's why we could have integrated fy, and then, or we could have integrated the y component and then tested it on the x component, but it doesn't matter which one you do, they'll both work. It's just sometimes one's harder or easier. I challenge you to do it the reverse way for this function, by the way. So f sub x or fx is dependent on y. That's fine. Yeah, so if it's conservative, you have to solve for a possible fy. Usually these would be easy to find, and there's usually a whole bunch of them that are possible if it is indeed conservative. But in general, yeah, but that usually just amounts to just taking the antiderivative. If f is conservative, then the negative partial of u with respect to y must be 0. Yes, precisely. All right. So what this implies, so z is eliminated because there's no z here, there's no k hat, so we can just not worry about it. In general, you would have to worry about it, but it makes the problem a little bit harder because then you might have to solve a partial differential equation. But in this case, it's two-dimensional, so we don't have to worry about that. Maximus, so I answered that already. The reason we do that is because the force given tells us what the x component is of the force and what the y component is of the force. The x component is a times x times y. The y component is 0 because we can just look at the force and see what the components are by reading off the coefficients of the unit vectors. So the point is so f prime of y, if f prime of y was, say, 1/2 ay squared, then it would work because there are functions whose derivative are 1/2 ay squared. There are functions that depend on y whose derivatives depend on y squared. We can't really do a demonstration of this with gravity because gravity is conservative. It won't work. It'll just spit out the potential energy function. But what this implies for this function, so it's not that there has to be a y in f prime of y. There can't be an x or a z in f prime of y because by definition, f of y only depends on y. There can't be x's present because by definition, f only depends on y. So the fact that the potential energy function u of x and y doesn't exist for the function f implies that the force f is not conservative. And so this is how you would check if a force is conservative or not. You would basically do this procedure. You would produce a candidate potential energy function. You would go through and force that it has to that everything has to work out, and then you would find that, but wait, there's a contradiction because the function that supposedly only depended on one variable actually depends on the other variable, for example. And that's a contradiction, so it means that your initial assumption that there was a potential energy function was false. All right. And I can do more examples of this after lecture and in office hours, but I do have to proceed here. Right, so we're still talking about potential energy functions, but we're going to slightly change topics. We're going to talk about equipotential surfaces. So an equipotential surface kind of should be what it sounds like. It's a surface upon which the potential is equal. Maybe I don't remember which pages. What's today? Today's the 26th. Yeah, no, actually, no, we probably won't. We probably won't get to impulse momentum. We're just going to finish talking about energy. That's fine. Yeah, so we'll be a little bit behind. That's okay. Right. So we're going to talk about equipotential surfaces. Maybe we can actually. Depends on how far we go. One moment. Yeah, so we might get to. I don't think that there are homework problems on it. Now you're making me nervous. So I didn't plan on getting to it, but no, there's no problem. There's no homework problems on it. Okay, anyway, let's talk about equipotential surfaces. Right, so they are surfaces on which the potential is equal. So let me explain. Or explain with an example. So suppose that we were just handed a potential energy function from someone. And let's just say that that potential energy function is a function of x, y, and z. So the force would depend in all three directions. This would be, and it's just given to you as negative a, where a is just some constant, x squared plus y squared plus z squared. It just is what it is. It just is that. So just a quick note, the square root of x squared plus y squared plus z squared is equal to the distance from the origin to the point x, y, z, right? Given some coordinates x, y, z, the distance from the origin to that point is given by the Pythagorean theorem, square root of x squared plus y squared plus z squared. So what does that tell us about this potential energy function? It tells us that every point that is equidistant from the origin every point like in the xyz space has the same potential energy. Because if they all have the same distance from the origin, then they all have the same distance squared from the origin, and then you just multiply that distance by negative a, and that gives you the potential energy, right? So it doesn't depend on like where, like your orientation relative to the origin, it only depends on the distance. So every point that is the same distance from the origin, those would all have the same potential energy. So what does that imply then? Is that rho, yeah, that would be rho. So that implies that points with equal potential energy, so every point that has the equal potential energy to another point, like if you have 2 points with equal potential energies to each other, points with equal potential energy must lie on the surface of a sphere. Now this is a yeah. So they have to lie on the surface of a sphere, right? Because if 2 points are the same distance from the origin, well, or the collection of all points in space that are the same distance from the origin, that's just defined to be a sphere, right? A sphere is the set of all points that are the same distance from some center. But well, so that's a surface. So equipotential, and they all have the same potential energy. Maybe we're going somewhere with this. We are. So given a potential energy, or given an energy, not like this is just some amount of joules, U naught. One can find a sphere. You have to assume that U naught is negative and so on, but you can find a sphere on which all points satisfy all points x, y, z. Those are the coordinates for those points. Satisfy the equation u of x, y, and z equals U naught. So what this is saying is it's saying you can pick some potential energy, or you can pick some value of the potential energy, say -5 joules. Then you could plug that in to your potential energy function, and you would find this, and that would tell you what the sphere is that is associated, or that would tell you the sphere that contains all of the points that have that much potential energy. So basically, there's a one-to-one relationship between these spheres that have potential energy and particular values of potential energy. So these surfaces, so the surface that, so you give a number of potential energy, -5 joules, and associated with that number is a surface. In this case, it's the surface of a sphere. These surfaces that are associated with that potential energy are called equipotential surfaces. So a way to think about this, it's kind of hard in 3 dimensions, is think like lines on a topographic map, right? So if you guys have ever seen like a topographic map of a mountain or whatever, the lines on the topographic map, they tell you all, like every point on the line will tell you that all of those points on that line have the same height. And each line will be associated with the height of the mountain, for example. And so if you think the height of that mountain is like the potential energy, and those points on those lines are like the equipotential surfaces, then you'd be perfectly right. In fact, that's an exact analog. The only difference is that we're imagining three-dimensional or three-dimensional surfaces, or the surface of three-dimensional objects, like the surface of a sphere, rather than an individual line. So these would be like, there would be a whole bunch of shells, and those shells each would have different potential energies on them. Now, we can also think about what the force would be for this potential energy. Well, I'm not going to do all the algebra for you. We can do this. We can just do the standard thing. So these describe combinations of x, y, and z. Well, yeah, it's precisely that. It turns out that this force is equal to 2a times xi hat plus yj hat plus zk hat. And you could prove, like, I'm not good, like, it takes a little bit of work to get here, but it's not so hard. But importantly, this vector points directly from the origin to the point xyz. So what we find is that the force vector points from the center to the point that you're evaluating it at. And that point also lives on a sphere. And so if you visualize this, think about it extra hard. It'd be like you have your point here, xyz, and your origin. The force vector would point this way. It would point from the origin to the point, and it would have some other, it would have some magnitude, but the direction is from the center. It is in the direction from the center to the point of interest. So the implication here is that the force points perpendicular to the spheres. Right, this is a right angle here. The force points away from the center of the sphere, and the sphere goes, not in that direction. So, in fact, everything that I've just described about potential energy functions actually generalizes nicely. Generally, or potential energy functions and equipotentials, a conservative force points perpendicular to its equipotential surfaces. Perpendicularly to its equipotential surfaces. So if you evaluate the force at a point somewhere in XYZ space, right, the direction that force is pointing in is always perpendicular to the imaginary equipotential surfaces that fill all of space. Like, you'd find the equipotential surface that point is part of, and that force would have to point precisely perpendicular to it. As another caveat here, just as something else that we can learn from this particular example, they also point from greater potential from higher to lower potential. Now let's just think about that for a minute. The force points from higher to lower potential. And so consider this. The potential energy function was negative A. We're assuming that A is positive here. So the potential energy function would tell us that as you get further away, isn't this for E and M? I mean, you'll use it in E and M, but this is just generally true. So as you get further away from the origin, the potential energy function gets more and more negative, right? It gets like, it starts off at 0, then it goes to -1, then -4, then -9, and so on as you get further and further away. And similarly, this force function, sorry, the force vector points outwards. So it points perpendicular to the potential energy function, sorry, to the equipotential surface. And like you had two choices for what direction, right? Inward or outward. But the direction that it points in is the direction towards the lower potential energy, i.e. more negative. It points towards the next potential energy function, which would be outside. And so it points in the direction that would lower the potential energy function the most. And so this is a general feature of forces. They always point in directions that will decrease their potential energy. So equipotential surfaces are a good tool for just visualizing how forces work. We'll touch on them a little bit more, but it's just something that I needed to introduce to you. There's one more tool that we need to talk about to understand systems in terms of energy, and these are energy diagrams. So what an energy diagram is, it's just a graph of the potential energy function in terms of position in space, of position in space. Now, typically you won't do this for all three coordinate directions, x, y, and z, because you need a fourth axis to visualize that. But you can do it for x and y, and then the third axis could be potential energy. Typically, we will do it for just x, like two axes. One axis will be the x direction, one axis will be the potential energy. And in addition to just graphing them, we also graph the total energy. So up till now, we've just been talking about potential energies just kind of in a vacuum, like potential energy of a force is whatever it is. But for a real system, like a block oscillating back and forth on a spring, that system has some amount of total energy. It has kinetic energy, it has potential energy, and so the total energy would be the sum of all of its energies. And so we would graph that total energy as well to understand that system. By the way, when we're talking about energy diagrams, we have to assume that there's no non-conservative forces. Assume no non-conservative forces. Just because there isn't a potential energy function for non-conservative forces, so we wouldn't be able to graph that. And so the energy would change even though it's not mirrored by the potential energy. It would just make things confusing. And so from these graphs, there's actually a lot to learn. You can learn a lot about the dynamics of the system just by looking at these graphs. So let's look at a simple case. Let's look at gravity. So we're just going to consider, I should move that down a little bit, an object under the influence of gravity. So in this case, the potential energy function, we're going to use the standard coordinates. So up is in the positive y direction. So the potential energy function for gravity is just mgy. And again, we could have added plus u naught, but we don't have to. And so for the sake of simplicity, let's not. Let's also assume that the block has, or that the object, whatever it is, assume object has some total energy. You also parameterize x and y to understand potential energy with respect to position. Yeah, that's precisely it. Yeah. So generally, you can do that. It just makes pictures a little bit more complicated. But yeah, you can totally do that. If you have like graphing software, like three-dimensional graphing software, you can totally do that. And everything that I'm about to say will generalize to the x and y to that case as well. So we're going to assume the object has some total energy, maybe like it's an object that's under the influence of gravity and it's falling. So it has some kinetic energy and some potential energy. Whatever it is, it's just like, if this was a problem, you would actually either figure out the total energy or you'd be given the total energy. But for the sake of this this example, let's just assume it's just given some amount of total energy. Let's call it E tot. And we're going to assume it's positive just because. No, I mean, not without changing your axes. Like you can't, like the potential energy, if up is the positive y direction, then mgy is the potential energy function. You could add some constant, but you can't change the function by like changing signs or whatever. Okay, so let's graph this now. So we have the y-axis, which would be height, say in meters, and we have this is the x-axis, which is y, and we have the y-axis, which is energy. I'll actually just put energy. So let's plot on this axis, let's plot this function mgy. So it passes through the origin and it's linear, so it just looks something like this. And so this would be u sub g, right? It's just a line, it's linear. And we were given that the total energy is positive, so let's just plot that function. So u sub g is obviously a function of y, so we can plot that. But the total energy is also a function of y. It's just a constant function of y, right? So we, just like how you can plot the number, like you can plot the function y equals 5 on your calculator, you can plot the energy function E equals E total. So in that case, I'm just going to use a dotted line to draw that. So the E total, let's just say it's this line. Okay, so let's now think about, actually, let me draw a slightly more illustrative line. So let's make it a little bit higher. I promise it'll make it easier to see what I'm about to do. So first of all, there's a special point here where the two lines cross. Now, what would that mean? It would mean that at this position, well, the total energy is equal to the potential energy. But the potential energy is equal to the kinetic energy plus the potential energy, right? So if that were the case, if the total energy was only potential energy, can the object ever get more potential energy than that? Well, I would say no. And the reason for that is because the kinetic energy can never be negative, right? The object is at rest. And so you can't get negative kinetic energy because the kinetic energy is 1/2 mv squared, which is always positive. So this would mean that this position, this height, y, is the maximum possible height that this object could have. Because that would be like, throw a ball up in the air, that would be the point where it's at rest and it's at its maximum height. At any other point, let's say this point, the object might have this much potential energy and this much kinetic energy. And so you could figure out the potential energy, like given some height y, you could figure out how much of its energy is kinetic energy and how much is potential energy given the total energy. As another thing to note, it's not that the potential energy is undefined, it's that the system is constrained so that the system cannot go beyond that point. Oh, cam froze? Okay. So something to note here is that the slope of this line, the slope of the line of this graph, this is du dy, right? And so that should be equal to the negative of the y component of the force, right? From the definition of, or from how we relate forces to potential energies. Now, the slope of this line is mg. So this is just mg. And so we would find that indeed the slope is the negative, or the magnitude of the slope is the negative. Sorry, no, just the slope is the negative of the force. Now, we can do a more complicated example. Oh, just one thing. So what direction does this force point in? So Fy is equal to negative mg. Well, if we were to draw force arrows that like tell us what direction the force points in on this graph, you would draw arrows that point to the left. Not down, but to the left, because to the left is, or so F sub y is negative, which indicates that the force should point in the negative y direction. And you can't like draw it pointing downward or at an angle because it has to point in a real world direction. Like there is no energy direction. There's height can have a direction up and down, but energy doesn't have a direction. So it just these force arrows always point horizontally. And so what you find in fact is that the forces point in the direction that will decrease the magnitude of the potential energy. All right, let's look at a more complicated example, the spring. So we're going to again look at a spring along the x-axis that has equilibrium at x naught. And so the potential energy function for the spring as a function of x is 1/2 k times x minus x naught quantity squared. And so the picture here is like you have your spring, you have your block attached to the spring. Maybe this coordinate is x equals 0. This position is x equals x naught at equilibrium. And maybe the block has some speed or something at that point. So we can again plot the potential energy function. So this is a quadratic function, so it'll look like a parabola. We also know that it's upright. And the last thing that we can learn from just by looking at this function is that it should be at its minimum value when x equals x naught. That's some pre-calc stuff. So if you're rusty, go back and double check on that. And we find that indeed the value of the spring potential energy is 0 when x equals x naught. So let's just draw this. So this would be x naught here, and then it's a parabola. By the way, note that I actually didn't extend the left side past the axis because the spring can't compress that far, right? It can go up to the axis and no further. Let's say that this thing has total potential energy. Oh, this would be the x coordinate, and this would be energy. This would be U sub spring, and maybe this is the total energy here. So it would have some total energy because it's moving when it's at equilibrium, right? So that means it has kinetic energy, even though the potential energy is 0. So what could we learn from this? Well, let's look at a single point. If the block was at this point, it would have this much potential energy, i.e., you would figure out however much that is on the axis, and the share of kinetic energy would be larger. And so actually, we can do the same thing that we did before, where we found the maximum possible value of or the maximum range, like how high the object could go in the gravity case. In this case, it would be how far can it stretch and compress the spring? Well, we would look at the places where the potential energy, I know I'm running over, I'll be done in a minute. We would look at the places where the potential energy function matches the total energy. So there would be 2 places here. In those cases, the energy is all potential energy. There's no kinetic energy there. So that would be, so the object can't go further than that. At that point, its speed is 0, and so it would just go back towards the equilibrium. So this would be x min, the minimum value that x can take, and this would be x max, the maximum value that x can take. And so right away, just by knowing the total energy of the system and where the object starts out, you can figure out the maximum and minimum amount that the spring can stretch and compress, because it's just given that's just given as when the total energy equals the potential energy. Now, just as a point of reference, or just as an aside, the equilibrium point for the spring, we've defined it to be when x equals 0, or x equals x naught. And just something that you might notice, the slope when x equals x naught is equal to 0, i.e. it's like horizontal, right? The slope there is 0. Oh boy. All right, should be good. Come on, scroll. So the slope is 0 at that point. But that shouldn't be surprising, because when the force is, or when the object is at equilibrium, there should be no force there. That's what it means to be at equilibrium. It means that the forces are balancing, or that there is no force. It's just happy to stay there forever. Now, we can also look at what direction the forces point in. The forces, you would go and you would take the negative slope, and you would find that on the left-hand side of x naught, the forces point to the right. And in fact, they get smaller as you get closer to equilibrium. And on the left, they point, or on the right, they point to the left. And they get bigger as you get further from equilibrium, which is, again, as expected, and that's definitely not the scale. These should be like about the same in size. So the point is that you can draw on these diagrams both the force, or the direction of the force, and the magnitude of the force, and that will tell you what direction the motion would be. So if the object is to the right of equilibrium, then the force will point you towards the left. Yes, so the forces do always point towards less potential. That's precisely it. And that was the point I was making with regards to the equipotential surfaces. All right, so I will end lecture now.